Now, while big cities are responsible for about 3/4 of the world's carbon emissions, a single construction material essential to every building accounts for more than 5% of those. It's cement. But a Melbourne company is developing an eco-friendly cement that promises to reduce carbon dioxide enormously. What's the fastest growing source of greenhouse gas? You might be surprised, but it's cement. Cement's already the third largest man-made source of carbon dioxide. More than 2 billion tonnes of it a year. That's after fossil fuels and deforestation. And because of all the construction going on around the world, cement's carbon footprint is growing rapidly. We desperately need greener concrete. Professor Jani van der Venter's team at the University of Melbourne has found one. And surprisingly, it's chemically similar to a cement used by the ancient Romans.
The good properties of geopolymeric concrete are also present in the old Roman structures. So old Roman concrete been made along very similar lines in terms of the chemistry.
Over time, the Roman knowledge was lost. The cement we know and use was invented in the 19th century. The problem with it is its fundamental chemistry. 60% of the carbon emissions from cement manufacture come from the chemical reaction required to make it. Calcium carbonate is heated until it breaks down into calcium oxide needed for the cement and the byproduct carbon dioxide. An environmentally friendly cement will need a completely different chemical reaction.
You have to change the intrinsic nature of the chemistry. Instead of having a calcium-based system, as is the case with normal cement, you have to switch the chemistry to an aluminium-silicon system. You use reactive aluminosilicate materials such as ash that comes from power stations. When you burn coal, ash is generated in huge quantities. And you can also use slag, which is a byproduct from the manufacturing of iron.
Jani's team explored the technique in the lab.
This is fly ash, which comes from the combustion of coal, so coal-fired power stations. Right. And we add to that also slag. It's a waste product from iron making, available in abundance throughout the world. I'm also putting in some sand, just ordinary sand that we use in normal concrete, because that is what we use as a filler. Then what we add is, this is just some water and also a little bit of alkaline solution, which turns this mixture of ash and slag and sand into a concrete, which will help to bind the particles together.
The activator dissolves out aluminium and silicon molecules from the slag and ash. These molecules then link together, forming much longer molecules. They're the geopolymers. The geopolymers themselves link together, creating a vast three-dimensional network. That's what gives the cement its strength, and no carbon dioxide is produced. Now, what we've just been seeing in the lab is happening here on an industrial scale. In fact, this concrete slab I'm sitting on is made from geopolymer cement. Now, looks like regular concrete. In fact, feels like regular concrete, and it seems as strong. There are 200 tonnes of storage silos being supported by this slab. Moving from the lab to the plant was not a simple matter, says Peter Duxon.
It's not just a case of taking a small thing and doing it on a larger scale. In the lab, we very rarely make concrete as such. When you move to making concrete, that involves rock and gravel, and then not only that, but the application of that product. So you need to work with contractors, and the way that the material is used becomes the critical factor.
The first steps in the process are identical to making ordinary concrete. Sand and gravel are loaded into a storage hopper, then sent to the cement mixing truck. Now comes the difference. Slag and fly ash from the silos are fed into the truck in carefully measured amounts. When the truck gets to its destination, the activator is added. The geopolymer concrete is then used exactly the same way as normal concrete. But it's all very well having a cement with a low carbon footprint. Is it any good? For example, will it do what ordinary cement does year in and year out? Well, it turns out a similar type of cement was developed in the Soviet Union in the 1950s and 60s.
What we have is that the Ukrainians have developed a concrete based on alkali activation, so the same type of chemistry as we use, but they've used only slag, not fly ash. So those old slag structures that are based on the same chemistry have been standing there for 45 years. And we have taken samples of those structures. We have published now work with the Ukrainians at the University of Kiev, and we have shown that these structures are strong, but we've also explained why they are strong and stable. So we have confidence that these materials will indeed stand the test of time.
When you consider how many concrete structures there are in the world and the fact that many of those will eventually have to be replaced, plus all the new concrete structures that could be built, you get the feeling that geopolymer cement could play a very big role in reducing our carbon footprint in the future.